All right. So, to recap what we finished with last week, we just finished proving the pumping lemma, which was how that we show a language is not a context-free language. So we had a simpler pumping lemma for showing that a regular language was not a context-free language. And then we had this more complex pumping lemma for showing that a language is not a context-free language. Okay? And we won't reprove it, but we'll review what it said. In essence, it said, if A is a context-free language, then there exists some number P, we call that number the pumping length, such that for any string in the language where the length of the string is greater than or equal to the pumping length, the string can essentially be pumped up. We essentially said long strings can be pumped up. Now, what do we mean by that? So, any string in the language with length at least P, there exists some way of dividing up the string into u, v, x, y, and z. So s is equal to u, v, x, y, z, that's how we're dividing up the string. There exists some way of dividing the string up into these 5 parts, such that the length of the vy part is at least 1. The vy part are the parts that we're going to pump up. So it has to have length of at least 1 in order for our pumping up to generate a new string. If they had length 0, pumping it up won't change anything. So the vy part have length of at least 1. This middle part, vxy, all together have a length less than or equal to p. And then finally, for any natural number I, u, v to the I, x, y to the I, z is in A. So any pumped up version of the string is also in the language. So, if s is a long enough string in the language, then the pumped up version of the string is also in the language, with those extra properties. Now note that what we proved is that being a context-free language implies you have this pumping property. We didn't prove the inverse. We didn't show that if you have the pumping property, then you're a context-free language. We said if you're a context-free language, then you have the pumping property. And so the contrapositive of this is if you don't have the pumping lemma, then you're not a context-free language. And so this is the way we typically use this property, is just to show that things are not a context-free language. So, what did the pumping property say all in one go, so that we can see the notation all in one line? It said that there exists some number p, such that for any string of at length p, there exists some way of dividing that string up into u, v, x, y, z, where the vy part has length at least 1, the v, x, y part is less than or equal to p, such that for any I in the natural numbers, u, v to the I, x, y to the I, z is also in our language. So now we need the negation of this for here. We need to know what not the pumping property is. This right here is what we mean by PP, the pumping property. So now we're going to write out what not the pumping property means. Not the pumping property means that for any p you choose, for any natural number p, there exists some string in the language of at least p, such that no matter how you divide that string up into u, v, x, y, and z, as long as the vy part is at least 1 and the v, x, y part is less than or equal to p, there exists some natural number I, such that u, v to the I, x, y to the I, z is not in the language. So if I can show that this second one applies to some language, which is not the pumping property, then I have shown that that language is not a context-free language, and that's how we use it. Okay, so let's see this in action. We're going to do a proof that A equal to A to the m, B to the n, C to the m, where n is a natural number, is not a context-free language. We're going to do this by proof by contradiction. So 1, assume by way of contradiction that we call it A, that A is a context-free language, comma, let P be the pumping length let P be the pumping length. So P is whatever this number is here. Since A is a context-free language, then there must exist some P such that no matter which string you choose of that length at least P, this is satisfied. So let P be the pumping length, or the length given by the pumping lemma, comma, and let S equal the string A to the P, B to the P, C to the P. So I'm trying to show this. I'm trying to show that for any P you can come up with, I can find some string of at least this length, such that no matter how you divide it up, as long as you divide it up this way, I can find some natural number in n such that I get a string not in the language when I pump it this way. Right? So I didn't get to choose what P was. That was something given to me. I do get to choose the S though. And that is the crux of these proofs, is coming up with the S. It's kind of like a proof by counterexample. Right?
And you don't get to choose how it's divvied up.
And I don't get to choose how it's divvied up.
But you do know that those two things are true, like Vy is greater than 1 and
Right. I know that however it's divvied up, it at least has to satisfy these two conditions.
Okay.
Right. Perfect. So the hardest part of these proofs is coming up with the string to use. So I need to be clever about choosing a string, so that no matter how this is divvied up, as long as you satisfy these conditions, if you pump up this string now, it's going to give me a string that's no longer in the language. So 2. How do I want to say the dividing up part? Oh, let S equal that, comma, and observe that, maybe we can make this its own separate thing, rather than extending this all out. 2. So since A is a context-free language, comma, then there must exist u, v, x, y, z equal to our string s, such that the size of u, v is greater than or equal to 1, and the size of vxy, not uv, sorry, vy, the size of vy is greater than or equal to 1, that, and the size of the middle part, vxy is less than or equal to p. 3. Since vxy is less than or equal to p, comma, it contains at least one letter, comma, and at most 2. In other words, since it has length p, it can be all a's, or it can be a's and b's, or it can be all b's, or it can be b's and c's, or it can be all c's. So it can contain at least, at most, 2 of the letters, and it has to contain at least 1 of the letters.
Okay.
So since vxy is less than or equal to p, it contains at least 1 letter, and at most 2. And at most 2, comma. And since the vy part is greater than or equal to 1, u v squared x y squared z is adds letters. What's the best way to say that? Is a string other than u, v, x, y, z, some new string. it changes the string if we pump it up in these forms.
Mm-hmm.
It adds a letter, so maybe I'll say the size of the pumped up version has a length greater than, strictly greater than, not greater than or equal to, strictly greater than when it wasn't pumped up, right?
Because VY also contains at least one letter, not most two.
No, VY can contain 100 letters.
No, I meant like different letters. Like it can contain.
Oh, I'm just saying, notice that VY, since that has at least one character in it,
Mm-hmm.
then when we pump up the V and the Y by one, we had to have gotten a longer string. That's all I'm saying.
Okay.
So we actually added something.
All right.
4. Then if Vxy, not absolute value, just Vxy, then if Vxy contains, I'll do like my lowercase a tall, so the S makes sense, A's and / or B's, comma, u v squared x y squared z has more A's and / or B's than C's, comma, so u v squared x y squared z is not in A. Right?
Mm-hmm.
5, same thing, has more B's and / or C's, comma, then same thing, B's and or C's, and same thing, more, this time we'll have more, making a mess out of it, trying to skip stuff, and I should just write it off. Okay, 5. If Vxy contains B's and or C's, B's and / or C's, comma, u v squared x y squared z is also not. Is not in A, same reason. Right? If it has more B's and or C's, or if Vxy contains B's and or C's, it's going to have more B's and or C's than A's. And so it won't be in A. 6. By pumping lemma, u v squared x y squared z is in A, contradiction. And so we're done.
All right.
Right? Let's do another one. This time write smaller so I don't get so cramped back. All right, let's prove another one. Let's prove that B is not a context-free language. And this time we'll have you come up with a string. So assume by way of contradiction that B is a context-free language, comma, let P be the the pumping length comma, and let S equal, maybe we should have gone over our language first. What's our language be? It's some number of A's followed by some number of B's followed by some number of B's, where we have more C's or the same number of C's as B's, and more B's or the same number of B's as A's. So the number of A's is less than or equal to the number of B's is less than or equal to the number of C's. Right?
Mm-hmm.
So we need to pick some string and then pick some way of pumping it that gets it out of the language. So what do we want to do? So what's the string that we might want to use for this? That's in the language.
The only one I can think of is like where I equals P and then J equals P plus
1
1 and then Q equals P plus 2. But if X, if the VXY is in like the second half of it, this B's and C's, then that doesn't really contradict it. But if it's in the first half, if it's in the A's and B's, then it would contradict it. So
You've got the right idea. So here's the string that we're going to use. It's actually going to be A to the P, B to the P, C to the P in A. Now, notice that satisfies it.
Mhm.
Now, if we're in the B's and or C's, we can pump down 1. We can get rid of the U and the Y,
oh, that's
or the V
right.
and the Y. And if we're in the first part, we can pump up 1.
Yeah, no, I forgot that you can pump down.
Yeah.
Like, you can pump down once, right?
You can pump down once, because you can get rid of it altogether. Perfect.
That makes sense.
So then there exists U, V, X, Y, Z equal to S such that the Vy part is greater than or equal to 1, and such that the Vxy part, xy part, is less than or equal to P. 3. Since Vxy is less than or equal to P, we don't say that. We'll just say then. I think we can see the logic now. So then, Vxy contains at least one letter, comma, maybe a better way to say it, then the, not the side of it, just the string, then the Vxy is composed of A's and slash or B's, comma, or B's and slash or C's, right? That's a better way to say it. We know it has to be composed of at least one of them because the Vy part has length at least 1, so this whole thing has length at least 1. And then since it has length at least P, then you already can see it's either going to fall completely within one letter, or straddle those two letters, or straddle those two letters.
Okay.
And then we just handle these two conditions. 4. If it's A's and slash or B's, comma, then uv squared x y squared z has more a's and slash or b's than c's, which implies uv squared x y squared z is not in A. 5, if it's b's and slash or c's, then u x z has less b's and slash or c's than a's, which gives us that u x z is not in A. 6. But by pumping lemma, uv squared x y squared z is in A, and ux z is in a contradiction. And so we're done. Right? Okay, let's try another one. Class 1, same process. So this is the strings of some string followed by the same string again, where the strings are zeros and ones. So, for example, this would be 1, 1, 0, 1, followed by 1, 1, 0, 1. So that altogether is an example of a string there. Okay, so we're trying to prove that this is not context-free language. 1, same thing as before, we all start the same way. Assume by way of contradiction that C is a context-free language, comma, let P be pumping length and let S equal, now what do we want for our string?
I don't really know how to write it, but I just want the length of W to be P.
You want the length of W to be P, but we got to be careful about what kind of W we consider.
That's true. If it's all zeros, my thing wouldn't work, so.
All right, we can't have it like a 0 to the P.
Right. I just want W to be really random. I don't know how to describe that in words.
To be really random. No, we need a particular W.
Let's have it be a bunch of zeros, P to the half times.
P half zeros, okay.
Yeah, like half of it would be zeros, half of it would be ones.
It's a thought. And that would in fact work. It's just hard to work with. An easier one to work with, which is your same idea, is just 0 to the P, 1 to the P for W. And then another 0 to the P, 1 to the P. It just needs to be length at least P. We don't need to get exact.
Right, okay. Yeah.
So this will accomplish what you were after,
Right.
and it'll be a little bit easier to work with. Okay, and let S equal that, which is in A. Okay, 2. Then there exists this u, v, x, y, z equal to s such that vy greater than or equal to 1 and vxy is less than or equal to p. Okay. Now we have three cases that we care about here. So the three cases we care about is vxy is in the first 0 to the p, 1 to the p, or it's in the second 0 to the p, 1 to the p, or it straddles the two.
Right.
So then vxy is in first 0 to the p, 1 to the p, second 0 to the p, 1 to the p, or both. Or in the 1 to the p, 0 to the p, 1 to the p, 0 to the p, that or the middle, or in the middle, maybe that's the easiest way to say it, middle 0 to the p, 1 to the p, right?
Isn't it 1 to the p, 0 to the p?
Thank you, yes. In the middle, 1 to the p, 0 to the p. Or if in either 0 to the p, 1 to the p, comma, then u v squared x y squared z makes 1/2 longer than the other. Longer than the other. So u v squared x y squared z is not in A. Right? 5. If in middle the middle part was 1 to the p, 0 to the p, 1 to the p, 0 to the p, then u v squared x y squared z either has more ones in first 1 to the p, or more zeros in second 0 to the p. If we pump up a string in here, we either increase the ones or the zeros or the both, or both. In either case, we either made these ones more than these ones, or those zeros more than those zeros. And so u v squared x y squared z is not in A. 6. By pumping lemma, u v squared x y squared z is in A. Contradiction. And we're done. Okay, so there's a bunch of examples using the pumping lemma to prove that languages are not context-free languages, very similar to the types of pumping proofs we've done in the past. Okay, so now shift gears a little bit. that takes care of that section. And the last section in this chapter, we're skipping over. Most people who do computation theory skip over this chapter, but it's one worth mentioning. And it is focusing now on deterministic context-free languages. So far we've just been considering context-free languages in general. This section focuses in on just and focuses on just a subset of them called deterministic context-free languages. So here you would use deterministic push-down automata. Our push PDAs that we were working with before were inherently non-deterministic, and we had multiple choices for particular input and particular stack symbol.
Right.
So there is a notion of a deterministic PDA, and there is a notion of a deterministic context-free grammar. Intuitively, a deterministic context-free grammar is one that's not ambiguous. That was bad. No, that's not necessarily the case. The nice thing about deterministic context-free grammars, one of the nice things about them, is that they're guaranteed not to be ambiguous. That's one of the nice things about them. They have a unique parse tree. Now, these are great for compilers or for parsers. So if you're building a programming language, and you're writing your own compiler for a programming language, then you want to use deterministic context-free grammars. And the way you want to reason about those is deterministic push-down automatas.
There was another machine that I am thinking of. I'm going to have to go back to it. So at the very beginning of class, we studied non-deterministic finite automaton. Is that what they were called?
An NFA, yeah.
An NFA. So how are deterministic push-down automatons different from deterministic finite automaton? Like, what's the difference there?
A DFA, a deterministic finite automata, was, give you a simple example of it. It would be something like this. We'll say 0, 0. Here's the accept state, here's the start state. Keep it simple. It accepts an odd number of zeros.
Mm-hmm.
There's no choice in the matter.
Right.
We have to put an arrow for every input and for every output. And if we wanted ones in here as well, we could say 1 goes to there, 1 goes to there. Okay. So it's just tracking whether we have an odd number of zeros or an even number of zeros. Mm-hmm. That's a deterministic that's a deterministic finite state machine. It's a DFA, a deterministic finite automata. A deterministic push-down automata would be where your finite state machine is a deterministic finite state machine, but you also give it access to a stack.
Okay, that makes sense.
We also have the notion of an NFA. That would be something like this. This is going to be a machine that accepts any strings that contain the substring 0, 1. And if it contains the substring 0, 1 anywhere in it, this will accept.
Right.
This one we have choices on what to do on a 0 in this location. So if we take a machine that starts out like this and then we give it a stack, now we're talking about a push-down automata. So adding a stack to this is a PDA, adding a stack to this is a deterministic push-down automata.
And when you have a deterministic machine, it can still have multiple accept states.
You can still have multiple accept states.
You can't have like any transition on epsilon, right?
No epsilon transitions for these. Yes, epsilon transitions for these.
Okay, that makes sense.
Okay, so yeah. So there is a notion of these machines. They're things that you would study more if we were taking, if this were a compiler's class, but compiler's class is its own thing. Mm-hmm. And so as you get your degree, you'll actually take a course on compilers itself. So that's why we don't spend too much time with these. It's a lot of work to prove what these things can and cannot do. They're one of those things that are very practical languages, very useful languages for the actual day-to-day programming that we use, but they're very ugly languages in terms of their theoretical properties. It's very hard to prove things about them.
I see.
Right. And so for a proof-heavy class like this, we try to avoid them because it just gets complicated. Okay. But just so you know, they are out there. There are such things, and they are very useful. Just hard to freak things about. And not really what we're interested in this class. Okay, so with that said, that ends chapter 2. And so just recap on where we are now with the end of chapter 2. Show us our hierarchy of problems once again to remind us of all this. So we start out with just finite state machines. This includes both this includes both DFAs and NFAs. It also includes regular expressions. An example of the type of language that can be recognized here is like 0 star, 1 star. Now we just finished the section on context-free languages.
Right.
Context-free languages, we can focus on what can be recognized by PDAs in general, or just by deterministic push-down automata. So what's a language that can be recognized by a deterministic push-down automata? Something like 0 to the n, 1 to the n. And you already have intuition for how you would build a machine that recognizes that. Push on a 0, or push a symbol on a stack every time you see a 0, and then pop off a symbol every time you see a 1. Make sure you're in the clear there. Give me an example of a language that isn't a deterministic one and some intuition for why you can't do it. This language, the union of 0 to the n, 1 to the n, and 0 to the n, 1 to the 2n. So we have twice as many 1 to 0s.
Okay.
Now this is real easy to do with a non-deterministic machine, because we can just build the thing that recognizes this, build the thing that recognizes this, and then do an epsilon transition to both.
Right.
The problem with trying to recognize this with a deterministic machine is when I'm popping off the stack to match my 1s with my 0s, I don't know if I should pop off 2 for every 0, if I should pop off 1 for every 0, or if I should pop off 2 for every 0s. There's no way to really communicate that and keep track of that.
Right.
So that gives you some intuition for the separation of languages there. And then languages that are decidable can be decided by a Turing machine. An example of that, 0 to the n, 1 to the n, 0 to the n. Did we do that one?
We did ABC.
We didn't do that one, did we? Yeah, but it's done almost identical to this, to the ABC one. Give you just the intuition for it really quick. 0 to the n, 1 to the n, 0 to the n. What's the S that we're going to use?
0 to the P, 1 to the P,
0 to the B, 1 to the B, 0 to the B. Perfect. And so your middle part has to be contained completely here in these two letters. Yeah, has to be contained in these two letters. And so pumping it up 1 is either going to give you more 0s here than 0s here, or more 1s here than 1s here. And then if it's contained completely over here, in one of these two, possibly both, pumping it up once makes more 0s here than here, or more 1s here than here. So that's how we improve it. Pretty similar. Okay, and so now I want to give you a notion of a problem that is undecidable, just to try and help start developing some sort of intuition for what these things are like before we work with them formally. So here's an example of a problem that is undecidable, and try to pick a simple one that's easy to understand. We're not going to prove that it's undecidable. We're not ready to do that yet. But it's just one that's easy to understand and can start giving you a sense of what it's like to work with these undecidable problems. So this is called the post-correspondence problem, very famous problem. And here's how the problem works. You're essentially given these two different sets of rules. So these sets of rules over here I'm going to call the set of rules for A. And these sets of rules over here I'm going to call the sets of rules for B. This is rule 1, this is rule 2, this is rule 3. For both of them. Now, the important part is that for every rule here, you have a corresponding rule over here. Okay. What are you trying to do? You're trying to come up with some sequence of numbers that makes so that the strings generated by both of these are identical. Let me give you an example. Let me try the rules. Give me rules numbers 1 through 3.
Like just a string of that?
Yeah, 1s, 2s, and 3s.
1 to 3.
So we'll try rule 1. So when we apply rule 1, so you say 1, 3, whatever, we'll do it. But first, when we apply rule 1, from A, we'll put A string here. We'll put B string over here. Maybe give A string more space. So A, when we apply rule 1, A has generated 1, and B has generated 1, 1, 1. Those aren't the same string. So now we try and pick another rule.
I'm confused. Can the rule only have, it can just be one of those?
You can pick, so far you've used just rule 1, right?
Right.
You can use rule 1 again if you want. So then if we use rule 1 again, then that makes A now 1 and B 1, 1, 1.
Mm-hmm.
Okay, now we try rule 2, and that makes A 1, 0, 1, 1, 1, and that makes B 1, 0.
Okay.
The strings still aren't the same. Is there some sequence of rules I can choose such that when we apply those rules in both these different languages, they generate the exact same string? Can I come up with some sequence of rules to make both these languages generate the exact same string?
I see.
And we already know now that we've gone down a bad path because we had a 0 here and a 1 here. So this sequence isn't working.
Right.
So now we need to try another sequence. So what rule should we start with?
Let's do 2.
So let's start with rule 2. So over here we have 1, 0, 1, 1, 1. And over here we have 1, 0. Okay, now what rule?
8.
Huh?
8, or sorry, 1.
1, okay. So now we have a 1 here and a 1, 1, 1 here.
Three, I guess. Sorry, I was trying to make them equal, but.
Yeah, if we try 3, then it's not going to work, right?
Right.
So let's not do that.
We do 1.
Do 1 again. So if we do 1 again, then over here we add a 1. Over here we add a 1, 1, 1. Okay.
And then 3.
And then 3. And this will be a 1, 0. That will be a 0. Those are identical strings.
Right.
So we found some sequence of rules that makes these two things generate identical strings. Now imagine that you are writing a program to do this. How might you write that program? You might have it try rule 1 by itself, and then rule 2 by itself, and then rule 3 by itself, and then the rule 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, etc.
Right.
And your program would keep on running and running and running forever until it found one. But how would it know that there isn't any sequence of rules?
It wouldn't.
It wouldn't. It would keep on running forever. So if it's possible, then you know your program will eventually stop. If I happen to give you a set that's impossible, then your program will run forever.
So what exactly is the problem here that a Turing machine can't solve? If you're saying like given 3 rules with an A and B section, then
Not necessarily 3 rules, but some series of rules, some arbitrary set of rules. Just make sure that there's the same number in both. And I want the Turing machine to answer the question, can these two, you can basically think about these as grammars. This variable can go to, you can see how you could easily make it into a grammar. A can go to 1, 2, and 3 all at the same time, and we add the option of what's a simple way to make that a grammar? You make so that you can replace the rule number with the string. And an A can generate another rule. Okay, that's how you would do it. So A can go to rule 1 with A again, or it can go to rule 2 with A again, or it can go to rule 3 with A again, and you also give the option of A going to nothing to just terminate it. Same thing with B, so you can think about those as 2 separate grammars. So the question is, can those 2 grammars generate the exact same string? It's kind of like the question you're asking.
okay, and you're saying that's something a Turing machine can't solve? This is an
So the Turing machine, if the grammars can generate the same string, if they can, then the Turing machine, through this brute force method, will eventually find that sequence. Maybe it takes 100 trillion rules to do it, But if we let our program run forever, it will eventually find that sequence of rules that works by just brute force trying every possible combination. Very stupid, very inefficient, but possible. And the program, given enough resources and enough time, will eventually do it. But what if there are no sequence of rules? How would the program know that?
It wouldn't. So some of these problems can be solved by a Turing machine?
So what it means for a problem to be decidable is if you give me a language, I can answer yes or no every time. We know how to write a program where it happens to say yes when the answer is yes. But our program won't know how to say no when the answer is no. So it can't decide it. Being able to decide it means to be able to answer yes when it's yes and no when it's no.
Okay.
Does that make sense?
But
There's a subclass of undecidable problems, which we call Turing recognizable, which are ones that are where it's able to say yes when it's yes, when it can at least do that.
But this general problem that you're talking about isn't necessarily a language. Like a chart is a language.
A chart?
I'm confused with the languages of these problems, like what that looks like.
The language of A?
You're saying if given a language, if you can answer yes when it's yes and no when it's no, then it's decidable. So what are the languages?
The decidable question, so in that case, the language would be all the strings that can be generated by this grammar and this grammar.
And then what's the question for all those strings? What's the question we're trying to answer, yes and no to?
What strings are in that group? What strings are in there? Are there any strings in there? Is there any string that can be generated by both this grammar and this grammar?
Okay, I see what you're saying.
And so when the answer is yes, we'll eventually find that string. When the answer is no, then that's a different question. So here's another example, and let's try it with this one. A's and B's, that time. What rule should we start with?
Probably 1.
Yeah, 1's the only one that makes sense to start with. If we start with 2, we already have a mismatch. That's 1 right there. If we start with 3, we already have a mismatch. So we do 1, and so here's A, here's B. With A, we'll have 1, 0. With B, we'll have 1, 0, 1. Okay? 3. So then we'll have a 1, 0, 1 here, and we'll have a 0, 1, 1 here.
And really only.
You can use 1 or 3.
I can't use
1 gives me, oh, you're right. Yeah, you can only use 3.
Using 3, but that's not going to work.
Yeah, so then you use a 3 again, and you get 1, 0, 1 here, and a 0, 1, 1 here.
And then I can keep using 3, but it's.
And then you can keep
the same
using
thing.
3 ad infinitum, and our program's never going to cease.
Right.
So maybe starting with 1 was a bad idea, but that was the only one that we could start with.
Yeah.
And so since this is never going to terminate, then you can recognize that this problem is one that it doesn't work for.
Right.
Now notice that we found a particular grammar where we were able to say no. So just because a problem is undecidable doesn't mean you can never decide given a grammar. It just means that there's no general formula to do it.
Like a Turing machine can't decide that the answer.
There's no program you could write to determine it for any 2 I give you. And so if I were to sit here and give you a bunch of these and have you determine yes, no, yes, no, yes, no, every time you said no, every time you said yes, it would be because you found some string of rules, but every time you said no, you are going to have to get some different piece of insight. So over here, as you were thinking about it, you said, well, this is the only one that we can start with, and it forces us to only continue with this, and since we're continuing with this forever, then the string generated by B always has 1 more character than the string generated by A. And that was some insight that you gained from this particular grammar. If I gave you some other grammar that didn't work for it, and you were to come up with a way to prove it didn't work for that one, it would be a whole new problem where you have to find whole new sets of insights.
Right. Okay.
So that gives you some intuition for what these undecidable problems are like. So undecidable doesn't mean we can never decide. It means that there is no general formula for deciding. And we'll prove that there's no general formula for deciding this right now. Or we'll prove it later. But for now, I just want to give you a feel for what it is like working with these problems and what we mean by undecidable. Because it's often the case that students get confused and they think undecidable means you can never decide. Which isn't what it means. It means given a particular problem, or it means in general, then there's no formula. But given a particular problem, you may or may not be able to solve it.
Okay.
Okay. So that's the hierarchy of where we're at so far. We're getting ready to jump to the next level, which is working with Turing machines. Before we do that, remind ourselves now of the closure properties and what we have shown, so what we know so far is and is not decidable. So closure properties. If I have a regular language, is a union of two regular languages regular?
Yeah.
Yes. Notice that union was one of our regular expression operations, so that was obvious. If I have two deterministic context-free languages, is their union regular?
No.
And the answer is no there. And to give you some intuition for why it's no, anytime we have to union languages together, we need that epsilon transition.
Right.
But the union of two context-free languages is. What about the intersection? For regular languages, it's true. If I have two regular languages, their intersection is a regular language. You might not remember how we proved that. But yeah, the way we proved that is we said, if you give me two deterministic context-free languages, one that tracks an even number of zeros, or an odd number of zeros, we'll do one that tracks an even number of ones. And then 0 goes back here, and 0 goes back here. We made a new machine that basically runs these two machines in parallel. We took the cross products of all their states, and we tracked basically both states simultaneously.
Right. Okay.
You remember that?
Yeah, no, I remember.
And so we basically took the cross product of those two machines, ran them simultaneously. That's how we do it with regular ones. Why can't we do the same thing with the deterministic context-free language? While we could with the inner states, we can't run two stacks simultaneously, because we only have one stack. And so it screws up our stack.
Okay, that makes sense.
And then same problem with context-free language. So because we have the stack there, that we can't take their intersections. A regular language minus another regular language, is it still regular? We proved that with regular languages. I don't have any good insight for intuition on why it's no here that I can think of off the top of my head. So just have to take my word for it, I guess. The complement. If A1's a regular language, is its complement still regular? Yes. How did we do that? We toggled all the accept states and rejects, all the accept states and non-accept states when it was written as a DFA.
It was written
As a deterministic context-free, or as a deterministic finite automata.
Are there regular languages that can be written with non-deterministic finite automata?
NFAs?
Yeah.
Yeah.
Oh, so.
Remember, NFAs and DFAs can recognize the same things. It just takes a lot of work to convert an NFA to a DFA.
Right, okay. I remember, yeah.
You can't do the same thing with deterministic pushdown automata. You can't convert a deterministic pushdown automata to a non-deterministic one and still have it be logically equivalent.
Isn't it technically, in my head I'm thinking DPDAs are a subset of just PDAs.
Deterministic pushdown automatas are a subset of pushdown automatas, but the set of all languages recognized by deterministic pushdown automatas is also a subset and a proper subset of all the languages recognized by pushdown automatas. So over here, in context-free languages, all the languages recognized by the non-deterministic version of the machine are actually more than all the languages recognized by just the deterministic. When we're inside here, finite state machines, the languages recognized by a deterministic finite automata and a non-deterministic finite automata, those are the same languages.
Right, you were saying that a deterministic push-down automata is, you can't make that into just a push-down automata. That's like automata.
Yeah. Oh, I meant that the other way.
Okay,
Sorry.
that makes more sense.
Okay, yeah. I meant you can't convert a PDA to a deterministic push-down automata.
Okay, yeah.
PDA. That's the way we can't go. I mean, you can always go the other way, yeah. Okay, so to convert this machine to its complement, I just toggle all the accept states and the non-accept states.
Right.
Same thing if we had a deterministic push-down automata. I can still now do the same thing since it's deterministic. But since a PDA might be non-deterministic, since there might be non-deterministic transitions, that no longer works. Okay. The closure of two of them, not the closure, the concatenation,
Okay.
right? This is A1 concatenate with A2.
And that means any string in A1
Followed by any string.
Okay.
Exactly. So if you have a regular language concatenated with a regular language, it's still regular. If you have a regular language, or sorry, if you have a deterministic context-free language concatenated with a deterministic context-free language, it is not necessarily a deterministic context-free language. Intuition as to why for that? It's because we need those epsilon transitions. We need to non-deterministically decide when we're done with the string in here and ready to start the string in here.
Couldn't the stack help us decide that?
In some cases, it might be able to.
Okay.
In some cases, it might not. Because the string we could be generating, so if we were doing something like 0 to the n, 1 to the n, followed by a 1 to the n, 0 to the n, this can be recognized by a deterministic context-free language. This can be recognized by a deterministic context-free language. Now, when I was trying to generate the string non-deterministically, this concatenated with this, I have no clue when the ends in this one end and the ends in this one start. Or I guess in that case I do, but
I mean, you would know when your stack is empty, right? You would know that we're moving on to the next string. That's that second half.
need a good example for this one. I get your intuition there. We could always make sure that the stack was empty when we were done, and then continue to the next thing. But maybe it was a string that we were supposed to reject. So maybe I generate a string like something like 0. How can I make it slip by? Here we go. Maybe I would have done something like 0 to the 5, 1 to the 4, concatenated with 1 to the 6, 0 to the 5. No, that's still fine.
I guess like we're not guaranteed that A1 empties the stack every time.
Yeah, it's going to be some problem with it emptied the stack and thought it could transition on, and so it thought it's reading along. If we had an example, it would be much cleaner. But it's like it's reading along the string. Technically, it's a string that shouldn't have gotten by. But it ended in a fine state. And so it shouldn't have gotten by because there was more input that ultimately should have led to it rejecting, but it slipped by anyways. Because it happened to just be in an accept state when the stack emptied out. And so it moved along even though there was more input for it.
But that extra input being pushed over to that second half, wouldn't that mess with the second half of the machine, make it not accept anyway, so it would be alright?
I need to come up with a good example for this. But the best intuition I can give you for right now, since I can't think of an example, is just that whenever we do these concatenations, it's always one machine, epsilon over, non-deterministically guess when we're at the middle, then the next machine.
Right.
Yeah, I need to think of a better example for that one. I know this is for sure right. So I know that's for sure right. I just need to come up with an example of it. So I'll have to think about that.
Okay.
And then for just context-free languages in general, since we have non-determinism, then yeah, we can easily do that. And then finally, reversal, we have it with all three, and we've done the reversal languages. We didn't do it here, but we did the reversal here, and we did the reversal here. Right?
Right.
Okay, and then decidability for these. Decidability. Can we decide whether or not the language is the empty language if the language is regular? So the language is regular, can I check that it's the empty language? It generates nothing. Is there a way to do that?
Yeah. If it's a regular language, can you check if it's empty?
Yeah. Can we check if it generates nothing?
I want to say like the empty set is a regular language by definition.
Yeah, we can convert it to, we can write it as a regular expression. The regular expression that generates nothing is that. If the regular expression for it is anything but that, then it has strings.
Right.
So that one's real easy. We can check if it's empty when it's regular. Deterministic context-free language. We didn't talk so much about those, so we'll skip over that one. Context-free language. Is there a way that we can determine whether or not that one's empty?
I don't know how you would check that a language is empty.
So for this one, we can convert it to Chomsky normal form, and then if it doesn't have any terminals, it's empty. Because we'll get rid of all our useless variables that end up going to nothing.
Okay.
The language generates everything. Can we check that? If it's a regular language, can we check that it generates all the possible strings in the alphabet? For a regular language, yes, that's real easy. How do we do it? See if its complement is the empty set. Since the complement of a regular language is still regular, then we just take its complement and see if it's the empty set. If the complement is the empty set, then it must be everything.
Okay, can't you also just have one state and it's the accept state, and so it accepts everything?
If you get that in a minimum form, yep, that's another way that you can do it. You might remember that we talked about every DFA has a minimum DFA.
Right.
But simpler way to do it is just, you have the language, take its complement. The complement of a regular language is still regular. If its complement is the empty set, then it must be everything.
Okay.
Similar thing with this. Since deterministic context-free languages are closed under complement, how do we know if a deterministic context-free language generates everything? Take its complement, see if it generates nothing.
Okay.
And then this one's a no. The reason it's a no is because it's not closed under complement.
But couldn't you write a machine where there's just one state and it's the accept state, and that's...
Oh, sorry. I'm not explaining this very well. I give you some language. I give you some context-free grammar.
Okay.
And I say, does this generate every possible string? So if I gave you some grammar and all the terminal symbols were zeros and ones, does it generate every possible string of zeros and ones? How would you check that with context-free grammar?
Oh. I don't know how you would check that with a regular one then.
With a regular one?
Like I'm trying to picture a machine that would check if it generates every single.
You don't need to come up with the machine. I give you the machine. And I ask you the question, does this accept everything? Now, if the machine I give you is a DFA or an NFA, so it's a regular language,
Okay.
then you can take the machine, right?
Mm-hmm.
You can take its complement now, which is toggle all the accept states and not accept states, assuming it's a DFA.
Okay.
You can now convert that to a regular expression and see if the regular expression is that.
Because you can convert the machine to a regular expression.
Yes, because regular expressions and DFAs logically equivalent. And we did some examples of converting regular expressions to machines and machines to regular expressions.
Okay, but we can't convert a DCFL to regular expressions, so or the machine that you're talking about.
Right, but there is a way for us to check if it generates nothing. And there is a way for us to take its complement.
How do we check if it generates nothing again?
We didn't go over an example of how to do that. So you just have to take
okay.
my word for it that we can check those. Again, we didn't do anything with deterministic context-free languages.
Okay, and how do we do that?
But it's similar to, huh?
I'm just wondering, how do we do it for a CFL now? Because I wasn't understanding before, so.
For a context-free language, how do we check if it generates nothing?
Yeah.
So I give you some grammar. What are the strings that that grammar generates?
Nothing.
Because a start can't reach a terminal. Right? If we converted this to Chomsky normal form, by the time it was all said and done, we wouldn't have any rules. Because we ultimately, in the process of converting it to Chomsky normal form, get rid of all the useless rules.
Okay.
The rules that can't be reached. But intuitively, that's how you check. Can you get from the start variable to a terminal? And you can always run it backwards for each of your terminals, because your language is always going to be finite, right?
Yeah.
So I can always check so I can go look for all my terminals, say where can you possibly come from B? Where can you possibly come from? Nowhere. Okay, next terminal. Where can you possibly come from? Some variable, which can come from some variable, which can come from some variable. And if you can ever find a path to start, then you're good. There's only a finite number to check, finite number of steps.
Okay.
So, intuition for how you could write some program to do it.
Okay, that makes sense.
So, how do we check? Ultimately, to check if the language is empty, can we eventually reach a terminal?
Right.
If we can't, then it's empty. If we can, we're good. Does it generate everything? Well, does its complement eventually reach a terminal? We can take the complement of these machines since they're deterministic. Let's just toggle their states. We can't with these since they're non-deterministic.
Okay, that makes more sense.
Are two languages equal? Yes for regular, no for these two types of grammars. Intuition for that is the post-correspondence problem. Checking if two grammars are equal is a lot like determining the post-correspondence problem. Do they always generate the same strings? Kind of.
What about for regular languages? Like if we have two DFAs, how do I know that they accept this same exact stuff? Is it like they have the same minimum or something?
We went over that. So we're talking about two regular languages, right? How do we check if they're equal?
Mm-hmm.
We check if language 1 minus language 2 is the empty set, and if language 2 minus language 1 is the empty set, which we can check those. And that's one that we did already. might remember that. Wow,
Yeah, no, I remember proving that. I'm just trying to remember how to write a machine that's like one machine minus another. Like.
We didn't write it as a minus. We wrote the minus in terms of these other operations.
Okay, that makes more sense.
In terms of the complement and the intersection.
Okay.
So that's how we did it. Is the intersection of two languages the empty language? For regular languages, yes, we can check that. That's real easy. For non-regular languages, we can't check that. Why can't we check that? Because we're not even guaranteed that their intersection is still the type of language that we're talking about. So a context-free language intersected with a context-free language isn't necessarily a context-free language. Give you a simple example of that really quick. If I have 0 to the 1, or sorry, 0 to the n, 1 to the n, 0 to the k.
Okay.
And then if I had 0 to the k, 1 to the n, 0 to the n. This we can do with a push-down automata. Just make sure the zeros and ones match up. I don't care how many zeros you have after that. We can also do this one. I don't care how many zeros, just make sure the ones match with the zeros there. Now take their intersection, now 0 to the n, 1 to the n, 0 to the n, which is definitely not a context-free language.
Okay.
So since the intersection of the two languages, we don't even know what that is necessarily, then we can't check to see if it's empty. There's intuition for that. Now, is a language ambiguous? Do you remember what it means for a language to be ambiguous, context-free language?
No, I did not.
Okay. So first off, there's no notion of a regular language being ambiguous, and there's no notion of a deterministic context-free language being ambiguous. That's the nice thing about these.
Okay.
Ambiguous meant that there were two different parse trees for the same string. And the example that we gave was, let's see if I can remember this. It was expression goes to expression plus expression, or expression times expression, or A, I think. And we came up with a parse tree, two different parse trees for A plus A times A.
So there's like two different ways of going through the machine and getting accepted?
No, there's two different parse trees in terms of the grammar. Nothing to do with the physical machine.
Okay, that makes sense.
And then we did an example of one that was not ambiguous, and it's one where we had the parentheses and always maintain precedence. You might remember doing that?
Yeah.
Yeah. So, context-free languages can sometimes be ambiguous. They're ambiguous if there's any string in the language, there's a string in the language, that can have two different parse trees to generate that exact string. Now that one is actually exactly the correspondence problem, because we can think about this as the grammar A. We can think about this as a grammar B, right? If I were trying to encapsulate both these as grammars, do that really quick, I could have A goes to A1, A, or it goes to A2, A, or it goes to A3, A, or it goes to the empty string. And then A1 goes to 1, A2 goes to 1, 0, 1, 1, 1, and A3 goes to 1, 0. So I'm converting those roles into a grammar now. And we could do a similar thing for B here. Then I could create a new grammar. So I could do S goes to A or B. And now, if I can determine whether or not S is ambiguous, then that means that there's two different parse trees for the same string. So if I can determine that A is not ambiguous and B is not ambiguous, and then put A and B together, and it is ambiguous, then I solve the correspondence problem.
saying you can't check if S is ambiguous?
Right, if it was, then we could solve the correspondence problem. And we know, you don't know yet, we'll prove it eventually, we know that the correspondence problem is not solvable.
Are you saying S is for sure not ambiguous?
I'm saying that, no, S may or may not be ambiguous. If S is ambiguous, then that means that there's two different ways to generate the same string. Two different parse trees for the same string.
That doesn't necessarily mean that those two different ways line up the rules the same, does it?
If they generate the same string using, oh, you're right. Because we need to be using the rules in the same order.
Right, yeah.
That is a good point. There is a way, using the fact that grammars are ambiguous, to solve the correspondence problem. Because yeah, then we're using different rules for each. That completely changes the problem. That is a good point. Okay, I'm only 80% sure that I have a proof of this somewhere now, but maybe I don't. I'll have to double check that.
And you're saying a proof that you can't
That
determine?
if you can determine if a context-free language is ambiguous, like if we had some, if we just assume that you have some magic algorithm for doing this, then it would be able to decide the correspondence problem.
And are you saying because you can't, then a context, there isn't any way?
Right, so if we could always determine that for a context-free language, then we could always solve the correspondence problem. But we will later do a proof that there is no solution for the correspondence problem, and therefore you can't decide whether grammars are ambiguous.
Is that like the way that, when I'm thinking of like how the computation theory is built, is that just the way that everyone decided to prove that that not all context-free languages are ambiguous, or like you can't prove that?
That's a common way that things are proved. So really what it is we do something like the halting problem.
Mm-hmm.
So the halting problem we prove flat out is not decidable.
Right.
Then we go and we get some problem like the correspondence problem. And we show that if the correspondence problem were decidable, that would imply that the halting problem were decidable. We find some algorithm that if this is decidable, our algorithm takes the fact that we have some magic machine that decides this thing. We assume there is some magic machine that solves this thing.
Mm-hmm.
And we use that magic machine to solve the halting problem. Since the halting problem we know isn't decidable, then our magic machine can't exist. And so there isn't a machine that can decide that problem.
Okay.
And so these are often reduction proofs is what we call them.
Okay, and it's pretty common for people to use specific problems to prove things generally about context-free languages.
Yeah, so you might have heard about NP complete problems. Have you ever heard about that?
No, I haven't.
Shoot. That's not one I can give to you in a short time without Turing machines.
But
We'll come across them, but yes, this showing that all these problems, showing that somehow solving this problem gives you a solution to this problem, that's very common. So in this book, rather than the halting problem, we'll do a logically equivalent version of it called the acceptance problem.
Mm-hmm.
It's almost identical to the halting problem. And it will be very common that we show that if we have a solution to some problem, that gives us a solution to the acceptance problem. We know that there is no solution to the acceptance problem, therefore there is no solution to this problem. And so the trick is finding out how, if there were a solution, showing that the solution to this implies a solution to this. If we can show that, then we're good. Because we know that there is no solution for this. Therefore, there can't be a solution for this.
Okay.
And that happens all the time. And then sometimes we show these back and forth. We show a solution to this, we give a solution to this, and a solution to this, we give you a solution to this. And so these problems are somehow logically equivalent. And so there's a big class of problems that is growing, which we call NP-complete problems, where a bunch of problems have been shown to basically be logically equivalent to each other. Mm-hmm. And all these problems are hard to solve. And it's one of those problems that if you came up with an efficient way to solve one of the problems, you would come up with an efficient way to solve all the problems.
I see.
Intuitively, at the heart of these NP-complete problems is the question, is it fundamentally harder to check a solution to a problem than it is to solve the problem? So for example, if I were to give you some multiplication problem, 1, 2, 3 times 4, 5, 6, and I gave you some answer to it, that was some plausible answer, 7, 8, 9, 0, 1, 2, how would you check if the answer was right? You'd actually multiply the problem out yourself and then see if that's the same as the answer.
So it comes down to the problem of like, which one's more efficient?
Well, no, so in this particular case, solving the problem and checking the problem are the same hard.
Right.
Me giving you the answer ahead of time does nothing to help you solve the problem any faster.
Yeah.
So checking the problem and solving the problem are the same hard. Now imagine I gave you a Sudoku and a completed Sudoku. Right? You've done Sudoku before?
Yeah.
Okay, if I gave you some completed Sudoku, so I had all the numbers filled out, and then I gave you a blank Sudoku and told you to solve it, which of those takes longer?
It's a lot easier to check it.
It's way easier to check it than it is to solve it. And that's the way it seems with these NP-complete problems. They're problems like solving a Sudoku. Solving a Sudoku is in this class. And so there is no proof that it is actually harder to solve a Sudoku than to check a Sudoku. And we don't know if that's actually true.
Oh.
For all we know, we're just really, really stupid about the algorithms that we come up with to solve Sudokus.
I see.
And it's not provable that there isn't some super efficient, or it has not been proven. It's one of the biggest questions in computer science. Checking a Sudoku is what we call an N problem. And then solving a Sudoku is what we call an NP problem. And so the question in computer science is P equal to NP.
Is like the
Is a set of problems that are like checking a Sudoku really the same as a set of problems like solving a Sudoku, or are they fundamentally different classes of problems? Is this a subset of this, or sorry, is this a subset of this, or are they actually the same thing?
Okay.
And that is the biggest open question in computer science, or at least one of the biggest open questions in computer science. And if it turns out to be equal, then basically all our encryption algorithms go out the door. Because all our encryption is based on the fact, well, kind of, good enough. All of our encryption is basically based on the fact that these are separate. It's all hanging on that. It's hanging on the fact that it's hard to factor a big number into its prime factors. Which is kind of like solving a Sudoku. And if you came up with some algorithm to solve a Sudoku really quick, then since that's shown to be NP-complete, your algorithm, people would already know how to take your algorithm and use it to solve all these other problems really quick. This massive class of problems. Because they already know how they're all logically equivalent. And so yeah, if you came up with a great way to solve Sudoku, you would be quite famous. But as far as we can tell, they're fundamentally different.
But we can't prove that they are?
We don't know if we can. It's an open question.
Right.
We have not yet proven that they're the same, and we have not yet proven that they're different. Now, most people are on the side that they're different. Seems that way. Sure, it feels to our intuition, but it's a little disturbing that we've yet to have a proof of it.
Right.
Anyways, not
You
sure
don't,
that
like,
can.
have a proof that there is no way to prove? I don't even know if that's the thing. Okay.
Prove that there is no way to prove it. So when you think about Gödel's theorem, Gödel's shows us that there are statements out there that it's provable that we cannot prove them. And we can prove that.
His statement just says that there are?
It proves that there are mathematical truths out there that we cannot prove.
Oh.
And he actually finds one.
He finds a mathematical...
He finds a statement that's true, that has no proof. And the statement is kind of like the statement, this statement has no proof. That's what the statement's kind of like. The statement, this statement has no proof.
And
Now, if the statement were false, then we'd have a proof for it.
Right.
Which means that the statement is false. So we can't have a proof for it, because that would be proving something that's false.
Oh.
You see?
Yeah.
And so the statement is true. Now, he comes up with a way of doing this. Basically, he reformulates all of math so that, this is exactly what he does, but it gives you the gist of it. He formulates all the axioms as prime numbers. So the first axiom is 2, the second is 3, the second is 5, the second is 7. And he's relying on the fact that any arithmetical number has a unique prime factorization.
Mm-hmm.
And so now the theorem that is implied by these two axioms together is 2 times 3. And the theorem that's implied by these two is 5 times 7. And the theorem that's implied by this statement and 5 together is the statement 2 times 3 times 5. Now it's more complicated than that, but that's just giving you intuition for it. You can actually follow his thinking. It's not that hard. It's just, it would take you 30 minutes to sit down and wrap your head around it and make it make sense.
Right.
But so through this type of generation, he comes up with a statement that has its big old number that is a non-provable statement. And it's the equivalent of coming up with some statement that says, this is a statement that cannot be proved. And so, if it could be proved, then the statement was false, which means it can't be proved. And so it can't be proved. So it's a true statement. And so some statement that we can identify as true.
I feel like his explanation of why that is true would be a proof that it's true.
It wasn't implied by the axioms. That's the disturbing thing about it. You can't take the axioms of the field and say, look at their logical implications, look at their logical implications, and look at their logical implications. It would never reach this new thing. And so this new statement of his has to then be included as an axiom.
And so it's just true, like, on its own.
Right, so if you want to include that in your system of mathematics, then you have to include that statement. Now he showed that no matter how many axioms you include, there will always be some statement like that. So if you want to prove everything, you have to have infinite axioms, essentially, if you want to be able to prove everything that's true in the field.
I see.
So the disturbing thing about that is there could be these problems that actually don't have a proof that people are working on. And we're trying to prove it with our set of axioms, and you just might not be able to prove it with our set of axioms.
So, like, we might need to, like, add another axiom, or is it like...
Or the thing itself that we're trying to prove might actually need to be included as an axiom.
Oh. And the only way we can include it is, like, if it logically makes sense to us, just like the one statement that...
Well, he just found that particular statement, but he showed that there were some statements that aren't so trivial that are also out there. So, for example, one of the big questions was, is there an infinity between the infinity of the integers, or the naturals, and between the infinities of the reals? So we proved in real analysis that these are two different size sets, right? Is there some set whose size is between those two things? That was one of the big open questions. turns out that you have to include as an axiom, if you want to talk about that, whether or not there are sets between there. There's no way to prove it from our real analysis axioms that there is some size in between those. And so the way that you have to pick your axioms is either there's an infinite number between those two, or there isn't any between those two, is the way it turns out.
Okay, but why would you accept something as an axiom without knowing for sure if it's true, and you can't know for sure if it's true?
Hold
Don't
on.
prove it.
Think about Euclidean geometry versus hyperbolic geometry.
Fair enough.
One says, if I've got this line, I got this point, there's only one parallel line to it. Another one says, no, there's infinite. Which one of those is true? It's not that one of those is true. It's which field of math do you want to develop?
Okay.
Similarly, depending on your choice here, you're developing one field versus another field.
And they
Because the field is just dictated by the axioms.
right, and like each one just has their own applications.
Potentially.
Right.
Yeah. Anyways, that's quite the tangent. I guess we can end it there since that's the end of a chapter. So we'll start Turing machines next time.
Okay.
Since no one else showed up, we'll cut it a little short.